Hello everyone. In this video, I'm going to introduce you the Canny edge detector, which is an edge detection operator that used a multi-stage algorithm to extract useful structural information of images. Among the edge detection methods developed so far, Canny edge detection algorithm is one of the most strictly defined methods that provides good and reliable detection. Although it was published in 1986 by John Canny, and people might use some new techniques in computer vision systems, but a lot of them are based on Canny edge detector by modifying some steps of it. So Canny edge detector is kind of a classical method that worth to learn. Basically, it contains 6 steps as I listed here. Each of the steps is very easy to understand. And as William always says, don't panic. I will explain all the details of them and give examples for better illustration. So, what exactly does Canny edge detector do? Is trying to find out the strongest edges of an image and get rid of the noise and the weak edges. In this picture of a flower, we kind of preserving the main structure of the flower and discard another flower, as well as the leaves in the background. In the final output, I also use different colors to indicate the directions which the edges are facing. Here is the overview of all the steps we are going to process. The first step is to turn the picture into grayscale. Yeah, you can do it separately for 3 color channels, but the output may look weird. And eventually, you still need to find a way to combine the results. Because what we want is just the edges, so grayscale is good enough. Secondly, we use a Gaussian filter to blur the grayscale image in order to reduce noise, which usually are high-frequency components of an image. If the picture is taken by a camera with very high ISO settings, the noise may produce a lot of low-level edges, which is not what we want. In the first step, we use the Sobel operator to find out the edges, horizontal and vertical edges, and put them together. What we want to know is where the edges are, but not how thick are they. So we will do a non-maximum suppression to preserve thin edges instead of thick edges. After that, Canny edge detector used a method called hysteresis thresholding. Actually, it's a two-way thresholding to preserve as many strong edges and get rid of the noise as possible. In the last step, we use different colors to indicate the angles or directions that the edges are facing. The coloring is shown at the top left of the image. I put the steps of the whole process in the above of the screen so you can know which step we are talking about and what we have done in the previous steps. Okay, and I will start to explain the details of each step, starting from grayscale. As you know, human eyes are not equally sensitive to all colors. Actually, human eyes are more sensitive to green compared to red and blue. The formula below is kind of the most popular equation that people used to convert an image to grayscale, while Y represents the luminance. Here are some examples of grayscale images produced by that formula: a flower and a Persian cat. In the second step, we would blur the grayscale image by a Gaussian filter. Gaussian blur is the most common blur, and the distribution of it looks like a bell curve. In most of the cases, it performs better than a mean blur. It's very common to use a Gaussian blur before Sobel operator to get rid of the high frequency stuff and keep the low frequency components, the main structure. This right-hand side kernel is used in this presentation. We use it to do the 2D convolution of the image and get the output. Because we want to keep the magnitude of each pixel as 1, so we sum all the values of the left-hand side kernel which is 159, and use it to divide the kernel. Here are some examples of Gaussian blur. The effect of Gaussian blur will be stronger if the image contains more high-frequency components, just like this donut. Sobel operator is the key to find out the edges. We use the kernel in x direction to calculate the horizontal edges, and the kernel in the y direction for vertical edges. The right-hand side kernel looks like the middle one, right? Which appeared in assignment 2. The middle one is a modified Sobel operator, in fact. I'm going to sketch the process of doing a kernel convolution in case of some of you may forget about it. Firstly, we need to exchange the values symmetrically inside the kernel. And let's say this is our image, and we want to know the output of this pixel. Imagine of putting the kernel above the image and multiply the corresponding values. -1 multiply 50, plus 0 multiply 50, plus 1 multiply 80, and so on. 120 is the result. After doing that, looking at the output image, the difference values between pixels are enlarged. Okay, in some cases, the values will be minus because they indicate the direction of luminance gradient. If we want to display the output, we need to convert them into 0 to 255. We need to combine the results generated by Sobel X and Sobel Y. If we want to find out the edges, a simple way to do that is calculating the square root of them. Then we would know where are the edges and get rid of the minus results as well. Gx and Gy respectively represents the convolution result of Sobel X and Sobel Y. As I mentioned previously, we want to know where are the edges are, but not how thick are they. So in the next step, we want to thin the edges by non-maximum suppression. The mechanism is quite simple. We want to preserve the pixels whose values is the highest among its neighbors and suppress the other pixels along the vertical direction of the edge. To do that, we need to know which directions the edges are facing. The method is very simple. The value of the angle phi can be calculated by arctangent Gy divides Gx. Gy and Gx are the results of Sobel operator. After knowing the angles, we divide the space into A parts and classify the angles. For example, edges whose angles between -22.5 degree and 22.5 degree are regarded to be horizontal. Preserving the highest values along the vertical direction of edges, we can easily produce an image with thin edges. Just like this. Okay, here are the examples: flowers, Persian cat, and donuts. After thinning the edges, we are going to decide which part of edges should be preserved and which part should be discarded by thresholding. The method being used in Canny edge detector is called hysteresis thresholding. Before explaining what is it, we should take a look at the disadvantages of one-way thresholding first. For simplicity, we use this coordinate system to show the relationship between luminance of some pixels. If we set the threshold here, preserving the pixels above the threshold and discard those below the threshold, like this. In some cases, it might work, but what if some of the pixels we discarded actually carry valid information, like the pixels on the red line? We do want to preserve them as well. Okay, then you might say, if we can lower the threshold like this, well, another problem comes up, that the pixels on the yellow line are noise actually. I mean, if some pixels carry valid information has similar luminance with noise, how can we judge that and preserve only the valid information and get rid of the noise? I do realize that it's a little bit abstract. Okay, so I prepare some practical examples for illustration. This image has been run through a one-way thresholding, and the pixels whose luminance are above the threshold are set to 255 as the white lights. Okay, while the other pixels look gray because their luminance are not high enough. If we pick a part of the image and enlarge it, comparing to the output of hysteresis thresholding, obviously we want to preserve the pixels in the red circle and discard that in the yellow circle. But we couldn't separate them by one-way thresholding because they have similar intensities. That's why we need hysteresis thresholding. We want to find a way to tell the computer which part or may contain valid information and which part are just noise, so it can optimize the image for us. Our purpose can be fulfilled by two steps. In the first place, we set two thresholds, a high threshold and a low threshold. The pixels below the low threshold are automatically set to 0, and the pixels above the high threshold are set to 1. 1 represents white, the same as 255. Okay, then we only need to deal with the pixels between the two thresholds. The mechanism is very simple. If all the neighbors of the pixel x are 0, then x is not connected to any valid edges, so it's set to be 0 as well. And if one of these neighbors is 1, okay, then x might be valid as that neighbor. In this presentation, we check the A neighbors of those middle pixels to decide if they are valid or noise. Of course, it's also fine if we check only 4 neighbors or more than A neighbors. Depends on what we need. In our cases, checking A neighbors is good enough. Look at these examples. Actually, we have done many experiments trying to find out a balance between information and noise. Honestly, angle indication is the easiest part. Remember, when we wanted to thin the edges, we calculated the directions which the edges are facing by arctangent gy divides gx. Take the result of that and map it to the coloring. Then the whole work is done. It's quite easy, but looks interesting in a way. Before the end of this video, let's review what Canny Edge Detector done step by step. Turn the images into grayscale. Use Gaussian blur to filter high-frequency noise. And find out the horizontal edges, the vertical edges, and combine them. Thin the edges by non-maximum suppression. Find a balance between information and noise by hysteresis thresholding. Finally, use different colors to indicate directions. This is the end of the presentation, and thanks for watching.